Go. Okay, good, thank you. So, welcome, my name is Robert Schiller. Working for data stacks. In the field as a solution architect committed to batching designer. Just a short recap about what ticket was about. It was about big partitions. Short recap 101 is when we read data, we go to room filter to bitmap, we go for the index summary, and then the primary index and the data. And 11.206 was about the primary index. Because what we have there is two kinds of object structures. One is the row index entry. It's for partitions that are relatively small, so say less than 64 kilobytes. And then extended implementation, that's the index entry, which comes into play when partitions get bigger. There's one index info object, so what we do is sampling across the partitions to make access to the data file much faster, because we can seek into the partition of the data file. The object structure in index entry basically looks like this, and it should only look complicated. It is complicated. It's a lot of pressure to GC. As an approximation, if you have 1 megabyte partitions, it's about more than 200 objects, maybe a couple of kilobytes. And the larger the partitions become, the more objects you have to manage. The GC garbage collector has to handle more objects, has to traverse the object tree, the lifecycle graph, and so on. It's not just about the size of the data in memory, it's also about the number of objects it has to traverse. So, after some initial implementation for the ticket, I did some local tests, and the other one is just with the previous implementation, and was about reading partitions of different sizes, so starting with a couple of megabytes, a couple of gigabytes, and in the end it just broke. Garbage collector came into play, and it just broke everything. And with the initial implementation, it went smoothly at around 1.5 gigabyte, and it was fine. So there were some issues with index entry. The object tree was also built during reads, but also during flushes. Flushes also come into play when you compact stuff, when you repair stuff. And it's also constructed for every read. It's not in the key cache. Every single object constructed there is put into the key cache and shared cache. So what it also did is, if you read a big partition, it was put into the key cache in the big cache entries. The initial approach was more like, okay, let's get rid of index info object in the key cache at all. So and then, if we need that, we just read it from this. We had some index offsets to the index file in the previous version for 3.0. But there was some not negligible performance degradation with some workloads. Then we came up with another approach that we keep these objects only if the partition itself, or rather the serialized size of the data in the primary index is below a certain size. And that's a new configuration parameter in the Cassandra YAML file. It's called column index hash size in kilobytes. That's a tunable thing. Otherwise, no index info object. So if the serialized size of the index entry object would get bigger than the 2 kilobytes in the default setting, none of these index info objects will stay on here. For the write class, there's a similar implementation. So if the serialized size of the index entry object will be smaller than 2 kilobytes, everything will be carrying only. If it gets bigger, it will be serialized into the binary and just flushed to disk. So there's a lot less objects to manage for the garbage collector. Read patterns I've seen in while developing this stuff was, of course, we have binary search. So say you access some SQL row in a partition. It's just a binary search. It's very straightforward. But there are also some access patterns that revisit certain index info objects over the time again. Same report. So there's some kind of caching inside that makes it a bit faster. Another factor are sequential reads. So for example, if you scan the whole partition, or if you do a repair, compaction, and so on, that's not affected by the read. What is bias? Of course, there's seed pressure during reads. There's seed pressure during writes. So, as I said, maybe in the beginning, tested locally with partitions up to 8 gigabytes. On a local node in the stress test was about 280 megabytes, and on a 5-node cluster it was with about 770 megabytes. The cluster was constrained more by disk and network I/O than by CPU. So, some lessons I've learned about that is, depending on the workload, especially with bigger partitions, is increase the committal size in segments. Also, maybe concurrent compactors, depending on the disk capabilities, and also compaction throughput. Otherwise, we just, the SS tips will just pile up. T-cache can hold a lot more partitions than before. It does still take time and add a lot of pressure. Compactions and flushes get a bit less expensive, depending on the partition size. My opinion and recommendations that we currently communicate for the maximum size of the partition still apply. So this is not something like that we can't just not hold more data per node in a performing fashion. And most importantly, large partitions doesn't meet large CPU levels. Because what we do then, if you access it, you have to serialize the whole thing that you pass back to the client in basically a byte array and push that over the wire. So, while testing that stuff, I found some stuff. We can go into that into more details tomorrow. This is what happened during the testing. So, in the beginning, first hours went smoothly, and then GC just broke the whole thing. And this was not about big partitions. This was sorry, I got some, but it's direct memory implementation by just sucks. What we can do, and it's also already implemented. I know Mauro from that is that he added some stuff to make it, but we can work around direct buffer implementation. We could do the same thing in Cassava. It's a fairly minor change. Interestingly, an overload to that X node recovers from that situation. Feed X node does not. Monitoring stuff is a bit difficult. My initial attempt was to use Graph in this book. Just broke my apart in dependency management. I ended up using Prometheus, it's really nice. Used a kind of different approach with Fana.
You should try JMX, it's amazing.
Nate's point about customer stress is also very kind of just we acknowledge that Michael Schepur from Apple initially started the project about Gatling, combining that with CQL, more like coding some stuff in Scala, and you get some really nice with beautiful stuff, and you get all the metrics from Cassandra, the rating system, and the load test in one place. So there's also some default some changes I could maybe discuss with you tomorrow is about changing the defaults for the concurrent reads, writes, and so on. And also change the defaults for the native transport flags. Otherwise, what happens is that in some bad situations, none of threads will just climb up. Another thing I realized is that during repairs and compactions, the chunk page is just filled and for nothing, just evicted. Yeah. Some other proposal is about those resource consumers. So it's very nice to see which web tools really consume data. And this with respect to CPU time and application rate. That's it.
Thanks, Robert. Let's get Michael up.
Let me turn off the camera.